enter. Alright, I show my screen here. You guys can see my screen? Do you guys can see my screen? Boleh nampak my screen tak?
Can, yes, can see.
Alright, good. Okay, so today we will continue to Unit 3. Our Unit 3 is on minimization and Boolean function. Okay, actually we have 3 subtopics for this Unit 3. The core one is on minimization of Boolean function and combinational logic design. Also, we have the MSI circuit. And finally, some introductions on the VHDL. Okay, VHDL will be covered. This is just introduction, but VHDL you will go deeper in digital circuit design. Okay, digital circuit design is your next subject after this digital electronics. Okay, we will start with minimizations of Boolean function. Okay, in our previous lesson, we have learned that the logic circuit can be described using 4 different ways. Okay, namely by a set of the statements. Okay, this is from the Boolean expressions, by a truth table, and by the circuit drawing. Okay, and today in our tutorial 2, we will learn the cannot mapping or the K-map description of the logic circuit. Okay, this is the K-map is the most commonly used tools for in order we want to simplify the Boolean function. Okay, think of K-map is a system to map the Boolean terms out. A good analogy would be to imagine a ship lost in a sea. Okay, if let's say if the captain were to say that he is located near some rocky looking island, then he would be giving the precise location of the ship, and the rescue worker would have a hard time finding the lost ship. Okay, instead if he says that the location at 50 degree is, let's say the exact location is 50 degrees east and 60 degrees north, and then the rescue worker we can easily trace where the location of the lost ship. Okay, and we can use this coordinate, okay, as a similar system to for the K-map, okay, cannot mapping system that we will learn. Okay, we have the principle of K-map plotting. Okay, in previous tutorial, we have learned that the logic circuit we can describe using 4 different ways. Okay, by using the statements, expressions, and the truth table, and so on. And then now we will continue for this principle of K-map plotting. Okay, this is one way for simplifications for the Boolean function. It is then using the Boolean algebra for simplifications by grouping the adjacent cells as long as there is one variable is different. Okay, let's see truth table. This one is the truth table of 2 variables we have at A and B, and this is the output Y. Okay, first we will circle the first output. Okay, the one output. Okay, the K-map will have a size that is equivalent to the number of variables being analyzed. There is number of cells being analyzed is given by the formula of Y equals to 2 to the power of X. Okay, for the output whereby the X shows the number of variables here. That one is for the output. Okay, and this is being analyzed, and this is the total number of cells. Okay, for example, we have two variables mapping contents of 4 cells, then 4 equals to 2 to the power of 2. Let's say we have three variables contents of 8 cells, so we have 8 equals to the power of 3, meaning that 3 variables. Okay, so now we will continue of Boolean circuit to consider the possibilities that there might be more than one implementations of a specific Boolean function. Okay, we are particularly focused on the idea of simplifying the Boolean function in the sense of reducing the number of basic logic gates. Okay, especially when we are using, let's say for example, not gate, AND gate, or gate function. Okay, now we will learn the technique of transferring the first output of truth table to the K-map technique. Okay, this is the output. Okay, now we have two variables for the 4 cells, meaning that 2 to the power of 2, then we get 4 output. Okay, this is the K-map of two variable truth table. Okay, this is for if the B equals to 0 and B equals to 1. And this is when A equals to 0 and A equals to 1. Okay, this is standard representations of the K-map method. Okay. The K-map need to be simplified to fewer the terms in order to produce the simpler Boolean terms. Okay, for simpler Boolean terms, meaning that the fewer components are needed while we want to implement the equation. Okay, we want to make it the circuit is less complex. Okay, simplifications of K-map technique can do either diagonal or horizontal, and also for vertical. Okay, we have the simplify the following logic of the K-map technique. Okay, now we have, for example, we have three inputs A, B, and C. Okay. So now we have the Boolean function. Let's say this is the Boolean functions for the output X equals to B C bar plus B bar C plus A bar B. So we can transfer into this K-map table. Okay, remember that two cells are said to be adjacent if they are differ in only one variables and are next to one another in a vertical or horizontal. Okay. For your information, the adjacent cells are defined as the cells that are next to each other, and the basic principle is to circle the highest number first before we attempt the lower one. So this is the highest, and next is this one, meaning that for this one here it is 0. Okay. Okay, rule to make this circle is one. First is we circle what output that equals to 1, and then the cell in circle must be adjacent to each other like this one here. Okay, so this is the first group we have, meaning for this one is when A equals to A bar is 0, okay, and B equals to this one when A bar, this the B is, we can't take the B because it is changed from B bar to B. Okay. Whereas for this one here is also changing from C bar to C. So we only have this, the one that remain A bar. Okay, this one here. Okay, meanwhile for this one is for group 2. Okay, for group 2 is we have this is conflict. Okay, meaning C and C bar. Okay, we can't take this C, so it only we have A dot B bar. Okay, for this second group. And because the variables that has conflict will be eliminated. Okay, like this one. Okay, for this group, this has conflict for C and C bar, so we be eliminated this one. Same goes with this group here. Okay, B also will be eliminated because B is from B bar and B, so we can't use this one. That is why for this group 1, we only have A bar. Okay, for this one. Meanwhile, for this group 2, we have A B bar here. Okay, this is the simplified Boolean function for this truth table. Okay. It is actually due to the law of identity. Okay, due to law of identity when C dot C bar is equals to 1. Okay. And same goes here. B dot B bar is also equals to 1. Okay, so this is the simplified logic circuit of the Boolean functions. We have as this one here, NOT gate, and this is the AND, and this is OR gate for this expression. Next, we have the Queen-McCluskey method to minimization the Boolean functions. Okay, the simplifications of a Boolean equation using K-map method is simple and convenient as long as the number of variables is not more than 6. Okay, it cannot be exceed than 6. As the number of variables increase, it is difficult for us to use the K-map technique. Then we can use this Queen-McCluskey method. Okay. Okay, developed by W.V. Queen and this McCluskey developed an exact method to simplify the Boolean expressions, so called as their name, Queen-McCluskey method, okay, also known as the tabular method. Okay, in the simplifications of Boolean using the K-map, we have discussed that the adjacent midterm should be reduced, and then these midterm are reduced because they differ by only one variable. For example, we have ABC and ABC bar. Then we can reduce because only C variables is differ. Okay, it is clear that the midterm whose the binary equivalent differ only in one place, then we can combine to reduce the midterm. Okay, this is the basic of principle for the Queen-McCluskey method. Okay, this is our procedures. Okay, we have to list all the midterm in the binary and then arrange the midterm. Okay, according to numbers, and then we have to compare. If it is differ by one position, then put a mark and write in the next column. Okay, and then replace by this one, replace step 3, this tab, okay, by the resulting column, and continue this process until no further eliminations. Okay, meaning that we have to repeat these steps. Okay, this is for Queen-McCluskey. Queen-McCluskey actually will not be asked in our syllabus. Okay, next we have the MSI circuit. Okay, in these sections, we will focus on the multiplexer and the multiplexer. Okay, for these circuits are commonly referred to as the medium scale integrated circuit for the MSI circuit. Okay, first is the multiplexer. It is a switch that can quickly select between multiple users or multiple output. Okay, and then only one user will be, multiple input will be allowed at one time. Okay, despite that we have multiple input due to the multiple user. Okay, it is also a combinational of the logic circuit. Okay, has multiple input and single output. MISO. Okay, multiple input, single output is a MISO. It is memoryless device. Okay, this is example for 2-to-1 multiplexer. Okay, we have 2 input and 1 output here. Okay, select input, we have this one as select only one data. It is either we select for data input I0 or I1. Okay, and send the data to the output Z here for the output of multiplexer, this one here. So this is the truth table for this 2-to-1 multiplexer. Okay, when S is equals to 0, then the data is selected from the input I0. Okay, when S equals to 1, again the data we select from the input I1. Okay. And this is the logic circuit for the 2-to-1 multiplexer. Okay, we have internal circuit of a 2-input multiplexer. Okay, we have 1 inverter, 2 AND gate and 1 OR gate. Okay, this multiplexer select input from, it is either I0 or I1. Depends on the value of this select input. Okay, if this select input S equals to 0, then multiplexer will select the input from I0. If the the multiplexer will select input from I0. If S, the select input is equal to 1, then we select the input from this I1. Okay, the two input multiplexer is commonly known as 2 to 1 multiplexer or 2 to 1 MUX. Okay, MUX for the multiplexer. Okay, because it choose only one input from the two available input, either it is I0 or I0, depends on the S value. Okay, it is possible to create either 2, 4, 16 or 32 bits data input multiplexer with the correct number of corresponding select input. Okay, however, due to difficulties of creating a multiplexer with individual gates, a multiplexer is often packaged in the integrated circuit, okay, in a IC. Okay, this one. See, this is a combining of multiplexers to cater for more inputs. Okay, normally we use in a IC. Okay, this one here we have 2 units of 4 to 1 multiplexer combined to become 8 to 1. Okay, this one is 4 to 1, and this one is another 4 to 1. So by combining these two, M1 and M2, we have 8 to 1 multiplexer. We have 8 input, okay, 1 output. Okay, to implement the multiplexer with more than 60 input, okay, there should be provision for expansion. To cater more than 16 input, a multiplexer we can combine with another multiplexer. Both for these multiplexers will take turn to operate. Okay, the enable input determines which multiplexer is working at any one time. This depends on the enable input. Okay, for this 4 to 1, it has 2 select input. Okay, S1 and S2. Okay, two set of 4 to 1 create, we will create 8-1, 1-8-2, 1 multiplexer. Okay, these two will have 8 to 1 multiplexer. Now we have 3 select input, S0, S1 and S2. When we combine these two, we have 3 select input here. Okay, the active input will have a value which is the same as this output. Okay, previously we have seen how multiplexer can be made into data selectors, and the definitions of data selectors is the ability to take one input at a time depending on the combinations of this input. Okay, now we will continue how the logic expressions are handled by the multiplexer. This is, we have a figure for the implementations using 8 to 1 multiplexer with 3 inputs. Okay, this is, we have 3 input, S0, S1 and S2. Okay, with 8 input here from I0 to I7. Okay, we have 3 variables with Boolean function, multiplexer with 3 select input. Okay, the input of multiplexer corresponding to the given terms are connected to the VCC. And the other inputs are connected to the ground here. Okay, this one is connected to the ground. And the enable input E, we have this one, okay, is connected to the ground to enable the chip ABC, which is corresponding to the select input. Okay, this one is connected to the select input S0, S1 and S2 of the multiplexer. Okay, the opposite of the multiplexer we have, just now we have look for the multiplexer. Now we go for the demultiplexer. Okay, it is the opposite operations of the multiplexer. In previous subtopic, we have discussed that the multiplexer adds like a switch which select one data input at any one time. Depend on the combination of the select input S. Okay, this means that the multiplexer has many data input and many select input, but only one output. Okay, the correct data input will be seen at the input depending on the combinational of the select input. Depends on the S. Okay, which data that we will take turn. Okay, for this demultiplexer, okay, the output will be activated is made to be the same as the data input. Okay, in other words, okay, the demultiplexer also acts like a switch. Okay, the output will be activated is made to be the same as the data input line and depends on the combination of the select input. Okay, let's see this one here. Okay, this is circuit for demultiplexer from 1 to 4. Okay, 1 to 4 output. Okay, this is, we call it as the internal circuitry of a 1 to 4 demultiplexer using AND gates and inverter here. Okay, the demultiplexer is a combinational circuit which has a single input, many output. See more. Single input, many output. Okay, see, single input, many output. See more. Okay, it performs the reverse operations of a multiplexer. Okay, opposite from the multiplexer. It accepts a single input and send it to one of the output lines. Okay, we have only one output. Sorry, only one input. Okay, depends on the select input and then which output that will be operate. Okay, the selected output line depends on the combinational of these select input S1, S0. Okay, both for both multiplexer and demultiplexer can be waived to implement logic functions and the Boolean equation. Okay, next we go for the VHDL. VHDL is very high-speed hardware description language. Okay, for this one, we will be learned more on in the digital circuit design. Okay, very high-speed hardware description language. Okay, this language allows you to, we can model the digital system, okay, prior to the constructions of the physical circuit. Okay, we can use to describe the behavior of the structure and can be performed in the design of digital system. Okay, overall for this high-speed hardware description language, coding is an essential tool for digital counter design. Okay, enables the you guys as the engineers and designers to describe the counter's functionality and behavior, also to implement the design using hardware device. And also we can verify and modify the design as needed. Okay, to pick up the more advanced features of the language later on. Okay, this is the architecture. One of the key features of VHDL is its ability to model concurrent processes, which makes it well suited for the describing complex digital system. Also, VHDL can support the use of libraries of pre-designed components, which we can be used to speed up the design process and to reduce errors. Okay, we have example of generic coding. Okay, depends on what the microprocessor trainer board that we use in connections. For example, microprocessor, some of the example is we can use the Arduino board or STM32 board and many more lah. Okay, depends on the sheets of the board. Okay, so this is example for the coding. Must declare each of the port that we use. Okay, this is very important, port declaration. Okay, to declare the port and also the clock pin that we use. Okay, this one is for the entity code. Okay, now we have two input, A, B, and C is the output. Okay, so now we declare this port A, B, and C as the input. Okay, and X as the output. Same goes here. This is for half adders. Okay, this one is the architecture body, and this is the logic circuit. Okay, now we use the library IEEE, okay, for the parameters. Okay, this one is port declarations, and this is the for the operation. Okay, must declare the port first. Okay, same goes here. Port declarations, and this is the operations. Operations is here. Okay, this is a test bench for the full adder circuit. Okay, it recall from the library, and this one is the declarations part, and this is when begin, this is the process. Okay. Okay, we have few types of VHDLs. Okay, but this is the basic. Okay, behavioral, data flow, and structural modeling. We use for these three basic ways for the VHDL. Okay, this one is for the data type. So that's all. Okay, for VHDL, we will cover deeper in digital circuit design. I think in unit 2 for the digital circuit design. Okay, so that's all for the slides that we have for today. Okay, for like this one, okay, this coding will be covered in, we have the experiment. One of the, I think exercise 3 is on the coding for the logic design. Okay. Okay, anyone has tried to run for the experiment? I think for next week we can start by next Sunday 16. Okay, we can start by 9:30 AM. Normally it only took 2 to 3 hours to complete all the assessment. Okay, for the experiment session, it will be open sessions, meaning that once you have construct all the assessment, then you may leave the sessions. Okay, I will stop sharing. Is there any questions from you guys? Is there any question? Before we go to, I have for some summary, okay, what we have learned today on the K-map. Okay, we have different method used to simplify the Boolean expressions. Okay, the algebraic simplification technique. We have the K-map and the Klimek-Klasky. However, Klimek-Klasky is will be not asked in our syllabus. We only focus on the K-map technique. Okay, and the second one, we have the MSI circuit. Okay, more on the multiplexer and demultiplexer. Okay, and on the MSI circuit, we have learned on various type of multiplexer and demultiplexer, and also at the end, just now, we have on the introduction to the VHDL language. Okay, where VHDL will be covered more details in digital circuit design. Okay, is there any questions from you guys? Okay, I have shared in the attached file the unit materials for digital electronics unit 2. Okay, inside that there are lots of exercise and self-assessment that you may do. Okay, boleh tengok the card attached file in this Microsoft Teams. Okay, is there any questions from you guys?